looking in on a meeting which should start in a minute or so, and it should be an interesting one. Mrs. Knight is just finishing with the last-minute arrangements. This is Bob Bradley. He's an electrical engineer.
Good morning, Mary.
Oh, good morning, Mr. Bradley. Pleasant day, isn't it?
Yes.
Oh, are you going to have movies today?
I intend to.
Here's Jim Swanson, the finance man.
Good morning, Bob. Oh, hello, Jim.
Mr. Fellows, said I'd meet them on the first tee at 7 o'clock.
And here comes Bill Peters, the superintendent. That's Harry Thatcher with him. He heads up the commercial department.
Well, say, Saturday okay with you? I figured we'd start out sometime about, well, right after dinner. Morning, Bob.
Morning, Bob.
Bill? Harry? Morning, Jim.
Morning, Jim.
Good morning, Harry. Good morning, Bill.
And here's Clarence Hartley, an up-and-coming junior executive.
Morning, men.
Oh, hello, Clarence.
Hi, Clarence.
Hey, Robert, what you say, boy? Oh, going to entertain us today.
Hello, Hartley.
This is J.R., the big boss. Things should get started any minute now.
Good morning.
Let's listen in.
J.R.?
Morning, Good morning, J.R.
Morning, J.R.
Morning, J.R.
Okay, let's get moving. Jim, right after this meeting, I want to see you in my office and go over those statements I was telling you about.
Right, J.R.
Okay, now. Oh, Clarence, will you find out for me why my parking space is always filled with Thatcher's car? And if you need any help on that, Thatcher there will give you a hand.
Well, maybe it's because you've been coming in too late, J.R.
Well, we won't go into that subject now, or some heads will start rolling. Okay. Oh, I want to remind all of you that those reports are due Friday. And let's not use 10 tons of paper. All I want is a concise statement of each of your operations, not more than 2 or 3 typewritten pages. And get them up to Clarence's office on Friday morning. I want them on my desk by noon. Oh, Bob, at the last meeting we deferred talking about an appropriation you wanted. Let's take that one up now. Well, I haven't had a chance to go over all these papers. Suppose you tell us what you want it for.
It's for new equipment for our main switching center. We're overdue for this gear. Why, just about everything we've been doing...
Bob, wait a minute. What's wrong with the one we have now? Are we having any particular trouble with it?
Yes. That's the same question I was going to ask.
That gear was all right when it was installed, but we've outgrown it. So I was starting to say, let's not stretch our luck too long. Why, this gear is like a pile of dynamite that can go off at any time.
Now, just a minute. We've been using that switching center for years.
The switchgear Swanson is talking about was installed 25 years ago, and as Bradley said, it was adequate at that time. But according to Bradley's calculations, the old oil circuit breaker equipment is no longer capable of handling the severe short circuits now possible on his system.
We've never had any trouble. No accidents, no blow-ups. Oh, sure, there have been outages, but you've got to expect those. How come this thing has suddenly become a pile of dynamite?
Yeah, how come?
Not suddenly, gradually. In the past 10 years, we've more than doubled the load without adding sufficient interrupting capacity. And with the plans we have for next year to expand even more, I'm telling you we've just reached the point where this equipment is essential.
Yes, and I want everyone around this table to know this is no time to lay out money for anything unless it's absolutely essential.
Right.
Thatcher here has put in for additional personnel, and Pete needs new facilities.
You're all right.
Sure do.
Well, if we don't get this new switchgear, Harry won't need any personnel, and Bill's new facilities will be useless. The equipment we need is basic to our entire operation.
And it's quite an expense.
You can say that again.
It's not an expense, J.R. It's an investment, the best one we can make. And if we don't make it, and soon, we'll pay out many times the amount I'm asking for in damages and lost profits as a result.
Frankly, I don't see that.
This new equipment. What is it? What are we talking about?
I need new air circuit breaker units for our main switching center.
Bradley is describing the latest metal-clad switchgear with magnetic air circuit breakers. In these units, all parts are completely protected with grounded metal enclosures. They offer maximum operator safety. The new design and rugged construction of these breakers simplify installation. And ordinarily, one man can take care of all routine maintenance requirements. Another important feature of the gear Bradley wants is its building block construction. To accommodate future load growth, additional circuits can be added to metal-clad gear with a minimum of expense and downtime.
It's not much money, and this new metal-clad switchgear will provide us with the interrupting capacity we need. I'm telling you, we just can't get by with our present equipment. We haven't got enough IC.
What is this IC you're talking about?
Yes, what is it?
I'll let an expert answer that question. This old film tells the story of IC. Oh, Clarence, will you pull down the screen?
Righto.
I see you. See, you've got your sales pitch all worked out, Bob.
Nothing like a movie to break up the day.
Well, the man who gives the presentation in this picture is an engineer, Tom McCauley, who knows this story and how to explain it perhaps better than anyone in the country. Clarence, will you turn out the lights, please?
Righto.
Yep. Guess we're all set now.
It was about 2 centuries ago when Benjamin Franklin flew a kite and proved that lightning from the sky was the same as man-made electricity. It was in 1882 in the Pearl Street station in New York City when they closed the switch and sent power flowing to the lower part of New York City where 59 customers enjoyed for the first time light made by man. Since that time, 50 million customers have been added to the power lines. And they did that for 3 reasons. Number 1, they received a continuous flow of electric power. Number 2, they could turn it on or shut it off whenever they desired. And 3, they had adequate protection against overloads and short circuits. Let me take you to your home and tell you a little more about man-made electricity. In your home, you have a continuous flow of electric power. You can turn it on or off. You have protective devices. Of course, you don't have an ammeter in your home, but we put that in for one purpose, to show you that the generator will go all out in giving you its maximum amount of electric power. Now, first off, we'll turn on the light. You notice it just takes a small amount of current. And now we'll go to the toaster. That takes much more power. Now we'll create a short circuit. I have just replaced the fuses. They blew, proving one thing: they had adequate interrupting capacity. Now I have deliberately created in this system a weaker portion than the protective devices I have now in service. Let's create another short circuit and see just what happens. This brings me to my point that adequate interrupting capacity is one of the most important things in electric service, because this may happen in any part of the system and may result in considerable damage. Now, when talking about protective devices, the most important question is, are they adequate or inadequate? Are they capable of interrupting the maximum amount of power that can be delivered under short-circuit conditions? Let's take a closer look at the IC story. This is the IC story. I told you what can happen in your home if you do not have adequate protective devices. Now I'd like to take you to some places where they use a great deal more of electric power, and these conditions are far more severe. I would like to take you to a particular part in the electrical system of this particular plant, we'll say the industrial plant, and show what can happen in one typical place, and that's at the switchgear equipment, because all the electric power must go through it for control and protection. In this particular spot, you notice these little red imps. They are little red imps that are developed by mechanical stresses, and they tend to work in harmony with the current, but do get out of control when short circuits occur. And you have to be careful that the equipment is designed adequately, or those little imps become Frankenstein and may wreck any part of the system. And if they do become Frankenstein, they literally pull things apart. Let me show you this in another way. These stresses build up enormously at a rapid rate. Let's take a typical industrial plant. This yellow block represents 2,000 kVA, the normal capacity. This green block represents a short circuit current, 20 times the normal capacity. This red block represents the mechanical stresses, the square of the short circuit current. This yellow block represents the additional kVA capacity. This green block represents the additional short circuit current that can be developed. This red block represents the additional mechanical stresses. This is a normal current. This is a short circuit current, and these are the mechanical stresses that can be developed. It's not like steam. It's not like water. You can't really visualize them. These stresses are invisible. When this system was originally installed, only 3 individual buses were required to carry the load. However, as time went on, additional capacity was required, so more buses were added, bringing the total up to 27. The mechanical stresses set up in this system was so great that it was necessary to place wooden blocks in between the buses to keep them from being forced together and causing severe short circuits on the system. Remember, the stresses are equivalent to the square of the maximum short circuit current which can be developed in a system. In this example, we saw what happened to these stresses when the capacity of the system was only doubled. Imagine the magnitude of the stresses developed in a system when the capacity is increased by 8 times. And imagine the maximum short circuit current in this system, which the protective device would have to be capable of interrupting. Now I will show you a few examples of what happens when the protective devices are not capable of interrupting such currents. But before I do, let's review the primary functions of a protective device, or a circuit breaker as it is known. There are 2 functions. One, to open and close a power circuit under normal or abnormal system conditions. Number 2, to interrupt the maximum short circuit current which can be developed on a system, and then, if desired, be capable of being instantly reclosed to carry out its functions. Now for the examples. First, let's look at a circuit breaker which did not have adequate interrupting capacity. This was formerly an oil circuit breaker. When the system it was supposed to be protecting developed a short circuit, this is what was left of it. Now don't misunderstand me. There was nothing wrong with this breaker. It served many years without failure and could have gone on serving if the short circuit capacity of the system it was on stayed within the breaker's rating. But as the system's capacity grew, this breaker was forgotten. And here's the result. This could just as well have been a modern breaker. It too would have failed if subjected to short circuits beyond its capacity. I want to show you two more protective devices which suffered the same fate. You're looking at a breaker made of heavy steel. Seeing it now, you think it was shattered by a bomb. Here's another breaker that was subjected to currents beyond its IC. Now, I have been talking for the past few minutes about interrupting capacity, and if it seems that I have overemphasized the importance of adequate protective devices, it is only because in my 40 years' experience in all phases of the electrical industry, I have learned above all this one fact, that electric power is not only the power to do, it is also the power to destroy, if not properly controlled. If system capacity is increased, the interrupting capacity of the protected devices must be increased to handle the maximum short circuit currents possible. If it is not, only one thing can happen. The power system, any power system, that grows and multiplies without adequate protective equipment is headed in one direction. Ultimately, a short circuit will trigger it. Well, that is the IC story. The moral is, beware of inadequate interrupting capacity.
Now wait a minute. Just one more thing. This film clip shows an actual test of an old oil circuit breaker. It's going to attempt to interrupt twice as much current as it was originally designed to handle. Watch now. Short circuit is about to be applied.
Wow, man, that's a blow for you.
Well, there it is. Clarence, will you get the lights?
Sure.
That's interrupting capacity and what it can mean. Well, what do you think?
Well, as Peter says, this is all very interesting, but Bob, you're not really trying to tell us that our switching center is going to blow up like the one on the screen, are you? And as JR says, why, Well, this is no time to be spending a lot of money on anything that isn't absolutely essential. And as Jim Swanson says, we've never really had any serious trouble with our old oil circuit breakers.
Bob, is it possible we could have an explosion with our present switchgear?
Yes. And with this new load we'll be picking up, I'd say it was more probable than possible. You know, you can't keep adding and adding more power on a system and not expect something to give. And we've been adding for years. We've been just plain lucky. You can't fool around with inadequate interrupting capacity.
Uh-huh. Well, what's next?
Next. But what about the switchgear, JR?
What do you think?
Well, I'm no electrical engineer, but as Bradley says, this inadequate interrupting capacity isn't something to fool with. I think we ought to have this new equipment.
Right. And you follow through on it. After the meeting, check with Bob.
Right, JR. By golly, I really do think we need this switchgear.